In this presentation, I will talk about panel data models in R. Before you watch this video, please make sure that you have watched my other video called Panel Data Models. I have opened up the R script here and I have downloaded the data called JTRAIN and I have put it into my directory here and I have run the program, and these are the results that you see in the console window that are typically below here, the script. So today we will talk about different panel data models, including the pooled OLS estimator, the between estimator, the first differences estimator, the fixed effects within estimator, the dummy variables regression, the random effects estimator, and the Hausman test for fixed versus random effects. For this, we would need the following packages that we're going to be using. And we will start with reading in the data job training, JTRAIN.csv, into our data frame. And then we would be filtering some of the missing observations. So anything that has not available or is missing for the log scrap, which is going to be our dependent variable, is not going to be included in the data set. So these are the variables that we're going to be using here. From the data set, we're going to be selecting F code, which would be the ID for the firm, year, which is the year for the observation, log scrap, that's going to be the scrap rate for the firm. So basically we're thinking about productivity of the firm, total hours of training for the firm, dummy variable if the year is 88 or 89, and here we have whether the firm received grant this year or last year to improve these scrap rates. So with the next thing, we're going to use the data frame to show the structure. We're going to see the first 9 observations, and we're going to use the Stargazer to summarize the data. Here's how the data would look like. So here we have 162 observations, 8 variables. These are the first few observations here. You can see them here as well, the first 9 observations. So notice that here we have data on firms. So here the first firm has a code of 410523. And you can see that for this firm we have 3 years of data. The second firm has a code of 410538, and this firm also has 3 years of data. And the next firm, this is the code for it, and the 3 years of data. So because we have panel data, it would be very important now to keep track of both the F code, which is the ID variable identifying the cross-sectional dimension of the data, as well as the time dimension of the data. So these are the scrap rates. So notice that these are the same scrap rates for the same firm over time. So this is the scrap rates for the second firm over time, and these are the scrap rates for the third firm over time. This is the hours of training that this firm has had, and these are dummy variables for the different years and whether or not the firm has received grant this year and last year. So we can use the Stargazer to summarize the data. What these means are showing is that this is a mean across all the firms and over time. So in some ways, these means are ignoring the fact that we are dealing with panel data because they just take an average over both the cross-sectional and the time series dimension. So here, let's look at the number of observations for the data. And so for that, we're going to be, from the data, we're going to be grouping by F code. So this is the ID dimension in the data. And we're going to summarize N is the number of observations by F code. And here, likewise, we will be grouping the data by year, and we're going to be summarizing N, which is the number of observations. Okay, so this is what we're going to see here. So we now have If we summarize by F code, N would be equal to 3. So basically we have 3 years of data. For each firm, we have 3 years of data. But if we're summarizing by different years, if we're grouping by years, then we have 54 firms in each year. So this is how many observations we have in each year. These are the firms, and these are the number of years that we have for each firm. Okay, so now what's important in panel data is to summarize the overall variations, the between variations, and the within variation for the data. So the overall variation, again, is the difference of each of the variable value value minus the overall mean. Here for the between variation, we're going to have the mean for the firm minus the overall mean. And for the within variation, we're going to have the value for each firm minus the mean for the firm. Okay, so this is how this is done. So from the data frame, we're going to select all of our variables. And here we're going to be using function x, where this function is going to take this form. It's going to have x, the value, minus the mean of x. And here we are saying if it's not available, then remove equals true. So basically remove the missing observations so that we can calculate the average. So this is the variable minus the overall mean. So variable minus the mean of x is what we're calculating here. And we're going to be, again, using the Stargazer to summarize the data, and we're going to be omitting the mean data. Digit equals 2, we're going to summarize everything to 2 significant digits after the decimal point. So these are the different variations that we're going to be summarizing here. So this is the first one would be the overall variation, the between and within variation. So here is the standard deviation for each of these for the overall variation. For the between variation, what we have here is first we need to use the data frame group by F code. So we're going to be grouping by the firm code here. We're going to be selecting all the variables, and then we're going to summarize just the mean. So we just want to summarize the mean of it for the between variation. And then we're going to be dropping this F code from the variables, and then we're going to be summarizing everything. So this is the means that we have here, and these are the standard deviations that we have here. So for the last one, for the within variation, we're again going to be grouping by F code. But here the function x is going to be like x minus the mean of x. So now notice that because we have already grouped by F code here, this mean of x is going to be the mean for each firm. So that's going to be the mean for each firm, and this is going to be the value of the individual value of each firm. So now we have the value minus the mean for this firm, and that's called demeaning the data. So while this formula here looks exactly the same as the formula here, you see like how we're not grouping by anything here, so this will be the overall mean. Whereas here, because we already grouped by F code, this is going to be the mean of the firm. So this is why this is a within variation. So now let's go ahead and compare the different variations that we have here. So the overall variation is how it varies across firms and over time. This standard deviation shows how it varies from one firm to the next. So that's the between variation. And this variation shows how it varies within the firm. Okay, so now let's look at the log of scrap rates. So here for the log of scrap rates, we see that the standard deviation here is 1.43 for the between variation, and here the standard deviation is 0.45. So what we see here is that the log of scrap rates differs a lot more between the firms, from one firm to the next, than within the firms. That's where most of the variation here is. For the total number of hours worked, we see that 21.25 compared to 18.61. We just have just slightly more between variation than within variation. So this is again how we compare how much a variable varies from one firm to the next versus how much the variable varies within the firm itself. And that's how we can use these overall, between, and within variations to interpret the data. Okay, so now let's move on to the different estimators that we can use to estimate panel data models. The first and the simplest estimator that we're going to be using is called pooled OLS. And basically what we have here is that the model is estimated using OLS, the OLS estimator, and we're basically ignoring the fact that we have panel data. In other words, we're ignoring the fact that the data belongs to the same firm and it also varies over time. So here we are going to be using a panel linear model here. And this is the formula. So we're going to have log of scrap as dependent variable. These are going to be the independent variables here. We're going to be calling the data JTRAIN. And here index equals C. Here we have F code and year. So it's important that you tell R here, this is the F code. That is the group index or the cross-sectional dimension of the data. And year is the time index. So it's important that they know, R knows the cross-sectional and the time series dimension of the data. So here we have a model equals pooling, and here's how we're going to be summarizing this model OLS. So these are the coefficients here. None of them are significantly different from 0. So if we're to interpret a coefficient here, we would say that for 1 additional hour of total training, we basically across the firms and over time, we do not see significant decrease in terms of log of scrap rate because this coefficient is not significantly different from 0. Now, for the between estimator, we can basically use the same model that we have above, but here model would be equal to between. So basically we can just copy and paste, and here instead of pooling, we're just gonna have to put between. So that's the only thing that we're updating here. And then let's look at this between estimator here. So notice that when we use the between estimator, what effectively it's being done is that instead of these original variables that we have, each of them is replaced with the mean. So here we don't have the log scrap, but we have the average of the log scrap for each firm. This is the average of the total hours for each firm and so forth. So these are now the variables that we have here. So if we look at this coefficient on total hours, it's again not significant. But basically how we would interpret it is that for each additional 1 hour increase in total hours, we would be seeing a drop of 0.7% in log scrap rates from one firm to the next. So basically, if one firm has 1 additional hour of training more than another firm, they would see a 0.7% reduction in log scrap, 0.7% reduction in scrap rates. But again, this effect here is not significant. So this will be for between estimator. Next, we're going to use the take the first differences. We did this with the previous video. So what we're going to be doing here is that we're going to be using function x, where here we're going to have x, each of the values, and from the dplyr package, we're going to be using the lag x function. So here we're going to be doing x minus lag x. So this will be the value minus the value the previous period. So that's how we're taking the first difference. And we're going to call this difference here. And so now let's go ahead and use the data frame group by F code. So this is the firm code. And then we're going to calculate the difference in scrap rate applying this function here where we have difference of log of scrap rates. So what we are doing is for each of the scrap rates, we're going to be taking the value this period minus the value last period. Same for total hours of training, we're going to be taking this difference function would be taking the value this period minus the value last period and so forth. So notice that the reason why we need to group everything by F code is because we will not be taking legs across the firms, right? We just should be taking legs within each firm. So that's why it's important to group it. And here we're ungrouping the data again. So now here's the first difference is estimator. We're just going to run a linear model. And here we're going to have D of log of scrap, D of total hours, D of grant. So basically we're going to be running a OLS model on the first difference data. So instead of each of the original variables, now we have a difference of each of the value minus the value the previous year. And this is what this first difference is showing us. So here, these are the results that we see as far as estimation for the first differences estimator. Here we have several of the coefficients listed. And this coefficient here, we would say that if the total hours of training increased by 1 hour from one period to the next, then we would have that the scrap rates would fall by 0.3% for the firm. But this effect is not significant here in this case. Okay, so now let's move on to fixed effects within estimator. Okay, so how we do this is we're going to be updating the previous model that we have for OLS. We are going to be putting model equals within. So before we had either pooling or between for the model. Now we're going to put within. And effect equals individual. So we're going to be having actually individual specific effects in this model. So these individual specific effects that we talked about. So here we are going to, if we want to do it the long way and just call the whole model, we're going to use Penel linear model. Here's the formula that we have here. Data equals JTRAIN. We are pointing out to again, the group index and the time index. This is the cross-sectional and the time series dimension of the data. Model equals within and effect equals individual. So this is how we actually run a fixed effects within estimator. And let's go ahead and summarize it here. So these are the results that we see as far as the summary. So here we have for the total number of hours for training, if they increase by 1 hour for each firm over its mean, then we're going to see that the scrap rates are falling by 0.4% for that firm. And again, this effect is not significantly different from zero. But this is how we're going to be interpreting such an effect if it were significantly different from zero. So now a very important thing in this within estimator is that we use these individual specific effects here. And so if we want to summarize these individual specific effects AI, how we're going to do this is we're going to be calling the fixed effects here. We're going to give model fixed effects, these results. And here we're going to use type equals D mean. So this would be extracting the fixed effects using this fixed effects function here that we have. So this would be an element of the results that we see here for the fixed effects model. And then let's go ahead and see the first head 10. Let's see the first 10 observations of this fixed effects. So this is how these fixed effects are going to look like. So, so we would have for the first firm, the fixed effect is minus 3.28. For the second firm, this is the code of the second firm. We have 0.45. For the third firm, this is the fixed effect, and so on. So each firm would have a fixed effect that obviously does not vary over time, and it's something specific to that firm that makes scrap rates higher or lower. So that first firm has a log of scrap rates that are 3.28 lower than the average scrap rate. Here, the second firm has 0.45 log of scrap rates higher than the average firm. these log of scrap rates are 1.29 higher than the average rates for the across all of the firms and so on. So again, we don't know what it is about these firms that makes their log scraps higher or lower, but after we estimate the model, we can go back and say there's something about these firms that makes their log scraps higher or lower, and we can quantify these exactly by calculating these individual specific effects. And so these individual specific effects are also listed exactly here, and we can see which ones are actually significantly different from zero. Okay, so now, and we have again 54 firms, so we're going to have 54 fixed effects here, one for each firm. If we're going to summarize the AI, the individual specific effect, what we are going to be doing here is we are going to have a mean of 0. So that's by design, the individual specific effects are going to have a mean of 0. Okay, so this is how we estimate a fixed effects or within estimator. An equivalent way in which we can estimate a fixed effects model is by using a dummy variables regression. So here we could actually use and update the model, the OLS model that we estimated above, but then include plus factor of F code. This factor of F code would be generating dummy variables, one for each firm, and that's how we can use it. So, or alternatively, what we can use here is this is the long formula. All we have to do is, as I said, the only difference from above is just put plus factor of F code. So this is going to give one dummy variable for each of the firms. Of course, it's going to skip one of them, one of the dummy variables, so that we can make the estimation feasible. We always have to drop one of the dummy variables when we use dummy variables. And so everything else in this formula is the same. We're going to be using the pooling model to estimate. And so let's now summarize the model with dummy variables here. And so this is what we're going to see here for the dummy variables. So notice that in this model, what we see is in the beginning we have these independent variables. So they each have an estimated coefficient here, and so none of them are, except for this one, is being significant at the 10%. But here, the way we would estimate this model is that if total hours increases, then we would be having, in this case, we don't have significant differences in terms of scrap rates for the firm. And here's this factor F code. These are the dummy variables that are now included in the model. And we have a coefficient estimated in here for each of the dummy variables. So notice that actually the F code for the first firm, which ended up in 23, that was the F code for the first firm. Notice that that one is not included in here. Why? Because that coefficient is actually normalized to 0. And all of these coefficients here are with respect to this coefficient on the first firm that was normalized to 0. So the reason why we have different estimates here for these fixed effects, for these coefficients on the dummy variables, is because we have different normalization. So in this case, the coefficient on the first firm was normalized to 0, and everything else is interpreted with respect to that first firm. And what we have above here in the fixed effects within estimator is that they actually sum up to 0. So they're basically as a deviation from the mean, which would be normalized as 0. So we can, of course, obtain we can obtain the fixed effects from this model comparison to this model. There's a one-to-one relationship, but this is why they differ. So here we had fixed effects again that were equal to minus 3.28 for the first firm. You see that ends in 23 F code. The second one that ends in 38 for the F code is 0.45, then it's 1.29, and so on. These sum up to 0. But here, what we have as far as the F codes is for the first firm, which is ends in 23, and it's not here. That's a normalized to 0. That's why it's not here. And here we have 3.73, not the 0.45 that we had before. And for this one, we have, for the third one, we have 4.57 and not the 1.3 that we had above. So again, that's the difference between these. Now, a question arises next. What is the R squared in terms of these different models? And one of them actually shows, here we have the R squared of 0.92 using a dummy variable regression. And the R square, if we look back up for the within estimation, would be the R square would be 0.22, 0.23. So the question is, why are the R squareds different if these coefficients here are exactly the same and we are getting the fixed effects for each of them. So these coefficients being the same and fixed effects, why are the dummy variable, why is the R squared different? And the reason for that is the following. So here we're going to be calculating the R squared for the fixed effects estimator and the dummy variables regression. So here what we're going to be using is this. We're going to summarize the model. We're going to be summarizing this model again. And let's get the fitted values from here, from this model, call them y hat. And here, what we're going to be using is, let's look at the demeaned y. So here, for each of the we're going to be calculating y hat minus the mean of y here, and this is going to be the model sum of squared. The residual sum of squares is going to be the residuals from the fixed effects model that we're going to be picking here. And the R square is going to be the model sum of square divided by the model sum of squares plus the sum of squares for the residuals. So let's repeat the same thing for the model with the dummy variables that we have here. So again, we're going to be calling the fitted values from this model. We're going to call this y hat. Here, we're going to be extracting the y values from this model, basically the value of the dependent variable that we have. And here we're going to be summarizing the model sum of squares using y hat minus the mean of y. And some of that would be the model sum of squares if we sum the squared values of that. And then the sum of squares of the residuals, we're going to be picking up the residuals from this model, squaring them, summing them. That's going to be the sum square residuals. And the R square, of course, would be equal to model sum of squares divided by model sum of squares and the residual sum of squares. So these are the results that we would see here. So let's compare the two results that we have here. So here, notice that the model sum of squares is a number like 7, and the residual sum of square is 24. This is what leads to this 0.22 of R square for the fixed effects estimator. What we're going to see here is that the model sum of squares is 287 here. So it's not 7, but 287. And the residual sum squared is still 24. And this is what leads to these very high R square of 0.92 here as opposed to 0.22. So before. So we basically have the same coefficients and same, we can also come up with the same individual specific effects after estimation and so forth, but the R-squares are different. The reason for that is that the fixed effects within estimator, what it does is demeans the variables. So instead of using y, it uses y minus y bar. And this basically removes a lot of the variation from there. And so we see it as this variation in the dependent variable that we had before of 287 is only 7 when we demean the data. And this is the reason why we cannot explain a lot of the variation there with the fixed effects within estimator. Whereas here we still have a lot of variation for the variables that we could basically be explaining. So that's always one of the properties of the fixed effects within estimator versus a dummy variable regression. The R square is going to be much higher if we just use dummy variables regression to portray the fixed effects with. Okay, then the final model that we're going to be doing today is the random effects estimator. So this is appropriate when we actually have individual specific effects that are not correlated with the error term. And so we can estimate this model by updating the first one that we have. All we need to change is basically say model equals random, and random methods, we are going to use the Walhus random effects estimation method here. So alternatively, we can use the long formula here. Again, formula, this is the dependent variable, all of our independent variables. And here we need to, of course, point out the data set, and we need to say which one is the cross-sectional and the time series dimension of the data. And these are the only two things that are changed here. Model would be equal to random, and the random method, we're going to use the Walhus random method here. And so let's summarize this model. And these are the results that we are going to see here. So we have this coefficient here on total hours is being significant at the 10% level. So here we have that if total hours of training increases for a firm by an hour, then we're going to have that the scrap rates are going to reduce by 0.4% for that firm. And another parameter that is being estimated here is this theta parameter. And this theta parameter here is equal, the median of it is 0.79. So this theta parameter again shows how closely the random effects estimator is to either the fixed effects or the pooled OLS model. So here it's being much closer to the fixed effects estimator with a value like 0.79. So this is one thing to notice about this model. We can also calculate this random effects parameter theta, and the way to do this, we're going to be picking up the results from this model RE for random effects, and then we are going to be picking up the error components that we have here. And then we're going to be picking up the sigma square for the idiosyncratic term. So this is basically the error term. And then we're going to be picking up the sigma square for the ID term. So this is now the individual specific effects. So that's the sigma square for the individual specific effects. We're going to be using this formula that we talked about. And if we just use all of this and calculate that individual specific effect, that individual specific effect would be 0.79. And if you notice, that's exactly the same as this 0.79 that is listed here. So we can basically also manually calculating it here. So this is again sigma squared of the error term, 0.25, and this is sigma squared of these individual specific effects that enter into this formula to calculate these data. So again, our conclusion is that the random effects model is a lot more similar to the fixed effects model than the pooled model. Okay, the final thing now is the Hausman test for fixed versus random effects. So the Hausman test is used to decide whether to use fixed effects or random effects. The null hypothesis is that the fixed effects are not significantly different from the random effects coefficient, and the alternative is that the fixed effects coefficients are significantly different from the random effects coefficients. So let's first of all call again the results from the fixed effects and the random effects estimator that we estimated above here and just look at them one more time. So these are the results from the fixed effects and the random effects model. So these are being the fixed effects, and these are being the random effects model here, the results. And so my question is this coefficient here similar to this coefficient here? Is this coefficient here similar to this coefficient here? This is basically what we are comparing. Are the coefficients similar to each other? And so the Hausman test statistic basically compares how close these are to each other. And so when we are actually using the Hausman test, we're going to be calling the Hausman tests with this command here, and we need to give the results of the fixed effects and the random effects model. And so here we have, this is the model that is being estimated, and we have a p-value of 0.94. So here, because the null hypothesis was that the coefficients are not significantly different from each other, then this is our conclusion, is that the fixed effects coefficients are not significantly different from the random effects coefficients. So then the conclusion is that if the Hausman test statistic is insignificant, then we will be using the random effects estimator because it is efficient. And this is the conclusion that we have here in our case. We are supposed to be using the random effects estimator. However, if it turned out that this Hausman test statistic was significant, then we should be using the fixed effects estimator because this one is the only consistent estimator. Okay, so this concludes our discussion on panel data models.